As we speak, you're surrounded by countless particles. But how many particles are there? How many types? And what do those types mean for life, the universe, and everything? Well, if you've ever wanted to describe the building blocks of the mature world like a physicist, this video is for you. Zoom in to every particle. This is everything.
Every particle. So before we dive into all the types of particles, we need to know what is a particle. Well, it can be thought of as a relatively small or the smallest discrete portion of something. In a more physics framework, it's any of the basic units of matter and energy, such as molecules, atoms, protons, electrons, or photons. If you really dive into the weeds of what it means to be a particle from a physics standpoint, quanta has a bunch of definitions like collapsed wave functions, quantum excitations of a field, irreducible representation of a group, entity with many layers, vibrating strings, deformation of the qubit ocean, and what's measured in textures, all as ways of describing particles. None of those are particularly helpful, so I'm going to kind of distill things down and have my working definition as a relevant foundational unit of matter that may be elemental or composite. So that covers things that are composite, like protons, that most people would think of as a particle, and also elementary, like photons or electrons, which are also thought of as particles by most people. Now, if you look up types of particles on a web search, you're undoubtedly going to run into an image of the Standard Model, which describes 3 of the 4 known fundamental forces in the universe and classifying all known elementary particles. It may be some version of a table like this, or that, or even this elegantly conceived model like here. So isn't it just a matter of counting up all the particles and calling it a day? 6 quarks, 6 leptons, 4 gauge bosons, 1 scalar boson? Well, while the Standard Model indeed gives an accurate summary of particle physics, it isn't the whole story. Buckle up for layers of Pico intrigue.
At the broadest level, there are 2 types of elementary particles: fermions, which have half integer spin, and bosons, which have integer spin. A third type of particle, which is composite, that is composed of 2 or more elementary particles, is labeled hadrons. I have them in the middle here because they can include both fermions and bosons together. Now, outside these broad typings, there are characteristics that will further divide particles. They include things like handedness and color in some particles. Most particles also have an antiparticle, which is distinguished by charge. Then there also might be, in some physics theories, superparticles, but so far they're merely hypothetical. Other characters will be brought up as needed. Well then, what makes particles different from one another? 3 major properties that distinguish particles are mass, charge, and spin. So mass is measured in eV, or electron volts. Some models show particle mass by different size icons, but to keep things tight in this talk, I'll keep my particles all the same size and just note the masses as appropriate. Another property is charge. Charge can be positive, it can be negative, it can be also neutral, and charge can be fractional, which we'll see in things like quarks as a good example of fractional charge. Third one here, spin, aka a type of angular momentum, can be 0, half integer, or integer values. Not shown here. In some models, a hypothetical graviton would have spin 2. Now there are other properties like color, chirality, isospin, etc., and they'll be brought up as needed, but these are the big 3. To summarize, here are the particle groups I will cover. Fermions. First, quarks, then leptons. Next, bosons. Then the composite particles known as hadrons, via baryons, mesons, and atoms. And at the end, a grab bag of other particles, including more hypothetical particles, quasiparticles, dark matter energy candidates, and various others. Starting out with quarks, there are 6 initial flavors of quarks, as they're called: up, down, charm, strange, top, and bottom. And here are their symbols here. Here's some of the characteristics. We have, actually, it's often described as 3 generations. We have the first generation, up and down. They're relatively low mass. Up has a charge of plus 2/3. Down has a charge of minus 1/3, and the spin is the same. Then the second generation, and then third generation, the masses change. These get much more massive, but the charges and spins are the same. So there you go, 6 quarks. But it's actually not that simple. You see, quarks can also come in different colors. You can have red, green, and blue quarks. And this has to do with things with gluons and quantum color theory. We're not going to get into that. So you can have actually 18 different quarks. But actually, it gets even more complicated because you can have left-handed quarks and right-handed quarks. So not 6, not 8, but 36 different quarks when you take into account color and handedness. But it turns out it actually gets even more complicated from there. So we have these quarks here, but I told you something. I told you there's also antiparticles. So every one of these quarks has an antiquark associated with it. So we've got double the number that we started with. But actually, depending on some physics, it actually can keep going from there, because there's some theories of supersymmetry posit a superpartner boson for every fermion, so that every quark would have a superpartner known as a squark. So every one of these I could have shown here would have a squark companion. But you kind of see this, you see what I might even go in here, it might get even crazier than that. Every anti-squark would also have, or anti-quark would also have an anti-squark, bringing the total here to 144. Of course, the bottom ones here are only hypothetical, but that is a lot of quarks to think about regardless. So it just blows your mind, all the variations we've got here. Anyways, let's take a quick look with the characteristics. Here's our normal quarks, our anti-quarks. The only thing that changes is charge. So the anti-up quark has negative 2/3, and then the anti-down quark has plus 1/3. And you see the symbol here for anti-quarks is usually a bar over the letter. Whereas with a superpartner, the spin actually goes to 0. Whereas the charge remains the same. I really haven't been able to get characteristics about mass, so I don't know if they have the same or different mass. Presumably the same mass, but it's unclear. And then similarly, the anti-squarks would have different charge, different spin, possibly different mass. And then there's no actual symbol that I found for anti-squarks, so I just use the double bars as my own made-up symbol here. My own notation. With quarks out of the way, let's get to the other type of fermion, leptons. There are also 6. There's electrons, electron neutrinos, muons, muon neutrinos, tauons, and tauon neutrinos. And here are the different symbols for them here. You're probably familiar with the electron, and if you read about interesting physics stuff, you probably heard neutrino, though probably not the specific kind of neutrino. Anyways, big thing here is electrons, muons, and tauons. They have increasingly higher mass, but then they have the similar charge and spin. These all have spin 1/2, whereas the neutrinos have very small mass. I think physicists don't think they're actually massless, but they can't really measure it. It's just very small. And they're also chargeless, so they're very low mass, no charge, so they really don't interact with other matters. That's why neutrinos are passing through you all the time. So that is that there. And with that, let's move on to more nuanced leptons. Just like with quarks, you're probably thinking, okay, there's probably going to be variations, and you're right. Now, starting with handedness, it stops here because it turns out only left-handed leptons have ever been observed. I don't think there's any strong physical understanding right now that prohibits right-handed, that just have not been observed. So that's kind of an interesting thing here. However, we can continue with all the leptons having antiparticles shown here. And while you can call like this first one an anti-electron, it's classically known as a positron. And it's interesting here, though, I told you that we see that the neutrinos have antiparticles, which is interesting because neutrinos have zero charge. So how do you have something that have zero charge have a different charge and be an antiparticle? Well, it turns out there's something weird going on here where antineutrinos have the same handedness but opposite chirality, and that's their oppositeness that makes them an antiparticle. I'm not completely clear on that, but they do clearly have antiparticles. Then with that being said, we can go on to the supersymmetry particles. So just like quarks had squarks, leptons have sleptrons. And we can extend that madness even further to anti-sleptons that we got here. Remind you, of course, that these last two are hypothetical. Taking a look at the properties of these then, we have the original ones with our mass and charge. Then again, the antiparticles will have opposite charges. You see again here the neutrinos charge say to 1. There's a different intrinsic properties that are changing to make them antiparticles. With the sleptons, spin goes to 0 because these are actually boson superpartners. Mass, I'm not sure if that changes. And then for anti-sleptons, again, the symbol is the double bar I'm using of my own notation. Charge and spin are going to be different, possibly mass. With that, we've got to our other side of the fundamental particles. We have the bosons. So with bosons, there are photons, gluons, W bosons, Z bosons, and the Higgs boson, a bit of a celebrity in the particle physics world with discovering it back in 2012. Now, then a hypothetical one here is the graviton. Here's the symbols for all these. Now, it's interesting here that, again, the graviton is hypothetical, and it turns out, looking at some of these properties, that the Y boson negative one is actually the antiparticle of the positive one. And we'll see here, for example, photons, glutons, and if gravitons exist, they actually have they're massless, they have mass 0, and they're actually chargeless. And then all the bosons have spin 1. The Z and H boson have mass, they're actually really massive. I think some of these, also the W boson, and actually some of these bosons have a similar mass to like a strontium atom, an entire atom. So that's kind of crazy massive particles. They're all chargeless except for, again, the W plus and minus, which means all the chargeless ones actually are their own antiparticles. They're not like neutrinos, which had other intrinsic properties that you could have antiparticles of. They're their own antiparticles. So that's an interesting departure from what we saw with some of the fermions. So let's switch and zoom in on gluons, because gluons has a lot of interesting thing, because there's actually 8 different colors of gluon, because gluons are what combine quarks together and give rise to color in quarks. Anyways, but there's actually 8 gluons, and it's kind of confusing because there's 3 colors, and so you can have different combinations. You might think there should be 9 combinations, but it's not the case. I have some stuff in the references that go more into what the reason is, but essentially the different color changes as they're called in gluons go like this. You have red, anti-blue, because you can have an anti-color. Again, wavy hands at advanced physics things. You can have red anti-green, blue anti-red, blue anti-green, green anti-red, and green anti-blue, and then these like weird combinations of like pluses and square roots and all this stuff here to give kind of paradoxically 8 different gluons. Zooming out and including the photon along with the gluon, it turns out there's handedness involved with these two particles. They can be left-handed, they actually be linear, and then right-handed, so you can have three more sets of varieties here. Now there are more bosons I came across that I'm not sure if they're hypothetical or virtual or only exist in the early universe or whatever. They all have to do with electroweak symmetry breaking and sort of conceptual precursors of the bosons we do have. But this is what I ascertained. Their names, W1, 2, and 3, the B boson, the Higgs plus, and the Higgs minus. Turns out there might actually be more types of Higgs bosons. That's really off in the weed. I couldn't really get more on that. But anyways, here's the symbols. They're all actually massless, which is kind of interesting because the W and the Higgs boson are kind of massive, very massive particles. And then the charges can be anywhere between 0 and plus or minus 1. And then these ones have spin 1, while the Higgs bosons have spin 0, actually. To complicate everything further, as always, you can have the supersymmetric partners, hypothetical ones, so the photino, the gluino, the wino, xeno, Higgs xeno, and gravitino, which is like doubly hypothetical because the graviton is hypothetical, the gravitino is hypothetical upon hypothetical. Here's sort of the symbols here. I'm going to stop adding too much, too consistently some of the diacritic marks because it just gets too complicated. Anyways, I just colored them, these light green, as the supersymmetric partners. These are, of course, hypothetical. They're going to have different masses. I showed the diacritic symbols here. It's a little easier than to put them in there. The spins are 1/2, but the gravitino has spin 3/2. And you see now, you see that these are half integer spins because, again, the supersymmetric theory is that for every boson, there's a supersymmetric fermion partner, and then over when we were talking about fermions, they had supersymmetric boson partners. So things like quarks and leptons had integer spin, while these enos of all the bosons have half integer spin. So you can have different charge, which again would make the negative wino its antiparticle. The other ones would be their own antiparticles. But then there's also confusing things that's hard to fit in here. There's actually the neutralino charginos, which again, I'm not really even sure how they fit in here, but they can be neutral. I'll get the symbols here. They're all mass 0, but they can be neutral charge +1, and then the -1 is going to be the antiparticle of the +1, and they're all spin 1/2. So there you go. And then even more bosons, of course, those ones I talked about with electroweak symmetry breaking, they're going to have super partner hypothetical particles, so wino 1, 2, and 3, bino, Higgs xeno plus, Higgs xeno minus, and then the wino is going to 3 is going to be the antiparticle, and so is the Higgs xeno minus, all hypothetical, so on and so forth. Great. Overwhelmed yet? Perfect. Let's turn over to hadrons, the composite particles, and start with baryons. And these are, at least starting out, going to be very familiar things because these are what most matter is made out of. So we have the proton, the neutron, but then we get, well, some nice p and some n's, and they make up atoms. So that's pretty easy. But then there's actually other baryons that you've probably never heard of, like lambda and sigma and z and omega and delta. So there we go here. And so what makes them these different things? Well, actually, so protons and neutrons each are made of 3 quarks, up and down quarks. But then what makes these other baryons is more exotic quarks, those heavier generations like strange charm, top and bottom. So lambda will have different quarks in there. I'll kind of show you this here. This is easier. it'll have an up and a down quark and then something else, and that something else is going to be like a strange, a charmed, or a bottom. Whereas sigma is going to have at least an up or down, an up or down, and then another one like strange, charm, bottom, and also top. Z is going to have one up or down, and then two like one of the heavier ones. Whereas omega has all three heavier quarks. And then delta is kind of really weird, is that they're going to have either all up, all down, or two up and two down, which is confusing because you see these middle ones here. Well, that kind of looks like the proton and neutron, but turns out they have a different mass and a different spin and a different isospin than ordinary protons and neutrons. By contrast, I didn't show the mass here because things get kind of messy, but anyways, protons and neutrons have masses about 939 megaelectrovolts. Their mass is really indistinguishable, and then a different spin and a different isospin. Delta have these delta particles that look like protons and neutrons have higher mass excitations of the proton and neutron respectively. Though there's these delta plus plus and delta minus have no direct sort of nucleon analogies, because the word nucleon, meaning protons and neutrons, are called nucleons because they're found in nucleuses of normal atoms, while these other things aren't nucleons. Looking more in depth at these more exotic baryons, turns out lambda, sigma, z, and omega all can be, there's different compositions, but they all can be hyperons. Hyperons are baryons with one or more strange quarks, but not charm, bottom, or top. But not all these have those, because some of them, the different types of them have those. But delta aren't hyperons at all, because they only have up or down quarks. So anyways, there's a lot of different types of these, so I'm going to try to pierce them out. So one of the ways to distinguish them is by angular momentum. So some have angular momentum of 1/2, some have 3/2, and then there's also things with resonance structures. That's a little foggy for me, but essentially resonance are excited baryon states with short half-lives and higher masses. But anyways, let's piece out how these baryons can be kind of set up and whether they can be 1/2 or 3/2 angular momentum. So lambda can have charmed or bottom quarks. Sigma we have charmed or bottom. Z can have charmed. So these are the different distinguishments. They can be charmed, charmed prime, double charmed, bottom, bottom prime, double bottom, charmed, bottom prime. So there's all kind of the different variations. Same sort of thing here with omega, charmed bottom, double charmed bottom prime, double bottom, double charmed bottom, triple charmed, triple bottom. And then delta doesn't have any of those, but then going through these ones, lambda, both of these have 1/2 resonance, same with sigma. Z, all of these can have this resonance, and then all of these except for the triple bottoms can have 1/2 angular momentum. Then sigma, both of these can be 3.5, so they could be either 1/2 or 3.5. Z, these various ones, and then omega, these ones can all be 3/2 as well. So you can have a charmed omega with 3/2 angular momentum, or a charmed omega with 1/2, and so forth. So there we go. And delta just has 3/2 angular momentum. Of course, we're not done, because the rearing head of the antiparticle comes back up. For every proton and every neutron, there can be an antiproton and antineutron. Surprise, surprise. And the same is true for the rest of these. And of course, it's interesting because the antiproton will have a charge of -1, while these can have a whole range of the more exotic baryons have a whole range of other charges, so they'll just flip as it goes. Though neutrons, it's weird because you think, well, the charge remains 0, but then what's actually happening is it's because it's composite, it's made of anti-quarks, so it is really different from a regular neutron. The charge just ends up equaling out to be 0 still. Next on our hadron list, we have mesons. Now, I forgot to mention why baryons, our previous one, are different, or what makes them special. So baryons are composed of 3 quarks, or 3 antiquarks or whatnot, and then bound together by gluons, where mesons are made of a quark and an antiquark. So it's 2-particle composite, where baryons were a 3-particle composite. So the mesons, the typical mesons are pion, there's eta, there's kaon, rho, omega, which is not to be confused with the omega boson, and then there's phi, there's upsilon, and then there's a J psi, there's D meson, okay, B meson, which again not to be confused with the hypothetical B boson. And so here we go. Here's all the symbols here. And then they will have antiparticles, because antiparticle is just going to be the flip. So in a things like a pion, an antipion will have the flipping antiparticles. So it's a little bit confusing. I showed some of these in sort of broken brackets because they sort of like technically have antiparticles, but it's really no different, and I'll show you why. For example, so the pion can be different types here. So it can be positive, minus, or 0. And as you can see with the quarks here, they can be, it actually turns out you can actually have a couple of them also be instead of just a quark and antiquark, you can flip them. So you can see here that the antiparticle is the reverse here. So this was a regular up and then an anti down. And this one was a regular down and anti up. Though the ones in the middle here, you can see if you switch it, it doesn't make any difference. Same thing here with eta. You can see that, well, this is actually really complicated, and it doesn't, it's like an equation, not just two quarks. So that's weird, and I can't really go understand that, but maybe either example would be, let's see here, omega here. No, not omega, phi. You can see here it's a strange quark and an anti-strange quark. You can see that the antiparticle, like, well, if you just flip one to the other, they're like the same. If you just rotate it, just symmetric. So that's why, like, it's sort of trivial to say that these have antiparticles. But anyways, there's a lot of variations depending on what quarks and antiquarks are made up of the mesons. So there we go there. We are not done with hadrons. We also have exotic hadrons. So if baryons had 3 quarks and mesons had 2 quarks, or at least antiquarks, there could be other rarer, exotic, short-lived things. So you can have tetraquarks, which is 2 quarks and 2 antiquarks. So the sort of formula here is the lowercase ones are either going to be up, down, or strange quark, and the uppercase are charm or bottom. And there are confirmed tetraquarks examined. There's like X4140, X4274, X4500, and X4700. And they were, I think, 2 charmed and 2 strange. There's also the first experimentally confirmed tetraquarks was ZC3900. And then first found as a resonance structure was Z4430, and it had a charm, an anti-charm, a down, and then anti-up. There's also other possible candidates for tetraquarks, including X3872, Y4140, and these are more broadly called XYZ particles, tetraquarks, because that was how you saw I just labeled X's and Y's and Z's with a bunch of numbers. They're called XYZ particles because that's how they were named when they were first sort of discovered and trying to figure out what they were. Okay, above tetraquarks, you can also have pentaquarks, which are 5 quarks, or like usually I think like 4 quarks and an antiquark. And they can have a couple different configurations. I heard them say they're either a 5 quark bag or sort of a baryon meson molecules are like 3 and 2. So you can think about some of these things, especially like pentaquarks. Theoretically, you could have any sort of combination of the different 6 flavors of quarks, and I guess presumably spin and color. Though I don't know if it's not color, because color is in things like hadrons. Quarks all have to have different colors, anyways. Complicated, but you could have a lot of different combinations of just quarks flavors and possibly handedness, though there's only a few that are experimentally confirmed. There's like P plus C 4380 and P plus C 4450. I think those are the only 2 actually confirmed. They're both up, down, charm, anti-charm. Okay, and again with pentaquarks, you could have sort of the anti-quark version of this, where you could have all 4 of these could be anti-quarks, this could be regular quark, where the tetraquark doesn't quite work that way because it sort of just, it's symmetric. Another thing you can have exotically, which I guess maybe wouldn't be a hadron. Well, yeah, it would be a hadron, but not a fermionic hadron, just an entirely bosonic hadron, which is a glue ball. And it can be in either 2 or 3 gluon states. I think there's like 15 possible states given mass and parity. You can also have hexaquarks, which would be either 6 quarks. Of course, you could have 6 antiquarks. So there we go. And of course, could have an even split between the 2. But these are hypothetical. Hexaquarks have not actually been observed. Our final stop on the hadrons is I want to briefly talk about atoms. Now, atoms are really getting out of the particle and into chemistry, but when you think of particles, you might think of elements, atoms and elements as sort of particles. So I want to kind of end there, though there's a lot of variation. Of course, atoms will have a nucleus made of protons and neutrons usually, and then an electron cloud. And there are all sorts of different atoms. And what element type depends on the number of protons. But there can be difference in atoms depending on other characteristics like the number of neutrons and the number of electrons. So some names here. An isotope is an atom with the same proton but different neutron numbers. So you might have carbon 14 and carbon 12. So same number of protons, which makes it carbon, but then the neutron number is different. Now, if you have an isotone, it's the same neutron but different proton numbers, so those would be different elements. An isobar is the same atomic weight, the same number of nucleons. So if you have 2 different groupings and they have the same protons and neutrons, so if you have a carbon 14, but then you also looked at something that had more protons but less neutrons that balance out, it would be an isobar. And then finally an ion, so same number of protons and usually neutrons, then more or less electrons. So you can have a cation with a positive charge or an anion or negative charge. And there is currently, I don't know if this goes up here, doesn't look like it goes up all the way, but I think there's currently 118 elements. Most of the heavier ones are only been briefly synthesized in the lab. We even have weirder atoms to talk about. There's something called leptomic atoms. One of them is positronium, which is an electron and a positron that orbit each other. So looks like an atom, but there's no nucleus. There's even muonium, which is an electron and a anti-muon. Again, it looks like an atom, but it's weird because there's no like protons and neutrons in the nucleus. There's also something called true muonium with muon and an anti-muon, but there's those have not been observed. They're just hypothetical. There's also things that could be exotic atoms. There's something called R baryons, which would be 3 quarks and gluinos. So again, the supersymmetry partner of the gluons that normally put together quarks. The lightest, all sorts of different variations of that, of course. The lightest would be an up, down, and strange, and then a gluino. There's also SIMPs, which we'll talk about in dark matter, so I won't go into here. And then finally, we talk about the extended table, which is hypothetical, but the heaviest known element right now is oganesum, which is at 118. So let's see, where is it? It is right here. The problem with like trying to synthesize and find higher elements up in periods like 8 and beyond is that they're so massive, they're very unstable, so they decay right away in fractions of a second. So it's not even clear if some of these higher periods could be even physically possible, but there might be islands of stability, and that's sort of an active hunt of finding heavier elements, like maybe 126 or 164 are possible islands. Though there's definitely going to be a physical limit. You can't go on finding heavier and heavier elements forever. But as of right now, the hunt is still on. We have made it to the hypothetical realm. We've already talked about some hypothetical, but these are like really out there. So I'll list them quick and then talk about them even more quickly, hopefully. We have the axon and axinosaxon, the baryon, digamma, dilaton and dilatino, dual graviton, graviphoton, and gravascalar / radion. Here is some of these things here. If you see the italicized symbol, that means I've just made them up because they didn't have their own symbol. And then if they're in light green, that means they are a supersymmetric partner. I'm not going to do the red right here because these are all hypothetical. So the axon, first of all, it's possibly cold dark matter and help solve the strong CP problem. And then the fermionic superpartner of that would be the axino, and then the bosonic superpartner would be the saxon. And so anyways, it's not clear whether two, because I guess they're neither bosonic or fermionic. It's not clear. Anyways, there's the baryon, which is a WIMP category. We'll see that in dark matter again. And it's predicted in brain cosmology, not brain as in head brain, but BRANE. Digamma, it might be a Large Hadron Collider anomaly. Again, if I don't specifically put a anti-version of this or a superpartner, that means I just don't know enough about it, and I presume they don't. And then there's the dilaton, which will have a superpartner of the dilatino. It's a particle of scalar fielded in extra-dimensional theories. The dual graviton, dual of the graviton under electromagnetic duality. It'll have its own antiparticle. The graviphoton emerges as an excitation of the gravitational field, essentially a massive photon, includes vector force, and it might be the superpartner of the graviton, where the gravascalar radion, excitation of gravitational field, several particles in multiple dimensions, and it might be the superpartner of the graviton. So weird stuff all around. Continuing our list of hypothetical protons, we have the inflaton, the magnetic photon, Majorana fermion, the X17 particle, X and Y bosons, and W' and Z' bosons. Anyways, here is some of the either real or made up symbols for them. So the inflaton is a scalar force carrier that physically caused inflation in early cosmology. The K gives rise to standard Markov particles. I don't know, it doesn't look like there's a charge or antiparticle or superpartner. The magnetic photon is a mix of even and odd C parity states and does not couple to leptons like photon. And this is predicted by some theories of extended electromagnetism. Again, don't know about charge or superpartner. Majoron is a type of goldstone boson. The goldstone boson It's very interesting. From what I understand it, it's conjectured to mediate neutrino mass violation, and the Majoran would be itself antiparticle, though it's not clear if it has a superpartner. The Majora fermion, it's its own ordinary particle again, as opposed to a Dirac fermion. Most of the standard model fermions are this. It has a zero charge, and the only thing it could be would be then apparently sterile neutrinos, which I guess is another thing that we didn't come up yet. So here we go, sterile neutrinos as a hypothetical particle, which is also what they would be left-handed antineutrinos and right-handed neutrinos. Again, remember we didn't see any right-handed neutrinos or other leptons. So there we go. The X17 particle is used to explain anomalous measurements. It could be a vector boson and the force carrier for the fifth force, apparently, if fifth force exists. X and Y bosons can correspond to new types of force predicted by a certain grand unified theory to mediate things, and they would have to have a lot of mass and would take higher energy than we can currently create to experimentally like try to see if they exist or not. The W apostrophe and Z apostrophe bosons are hypothetical gauge bosons that arise from extensions of electroweak symmetry, and different theories give different numbers, since W can be plus and minus, and then anti and Z equals 0. So it looks like with some of these things here, the X and Y, they should be able to have antiparticles, while the W should also, but the Z, because I think it has a charge of 0, would have none. But all these hypothetical bosons should have supersymmetric partners, and then anti-supersymmetric partners if they have an antiparticle. We are still going through hypothetical particles. We have Higgs doublet, Kaluza-Klein towers, leptoquarks, mirror particles, magnetic monopole, and preons. So Higgs doublets, they're different numbers of doublets in different models. That's all I really know about them. Not sure about antiparticles or superpartners. Kaluza-Klein towers, they're predicted by some models of extra dimensions. I think there's many kinds. They're sort of precursors of string theory, and they have, I think, 5 dimensions. Leptoquarks, they interact with quarks and leptons, and there could be different, I think, angular momentum, and then, of course, anti-leptoquarks as well. And there'd be color triplet bosons that carry both lepton and baryon numbers, spin, charge, and weak isospin, and they vary among theories about leptoquarks, but they should decay into quarks and leptons. It's unclear if they would have superpartners as well. Then there are mirror particles, aka shadow or Alice matter, like through the looking glass, and they're positive to deal with mirror reflection symmetry, also known as parity. And so in this conception, every particle would need a mirror particle, except the graviton, which would be identical. And there would be weak interaction with other matter, so this could maybe be dark matter. But in any case, you think about all the particles we've talked about, like quarks, then antiquarks, then squarks, then anti-squarks, with different handedness and color and all that stuff. And imagine that you take all those things and then you double them again because of the mirror particles. It's like, yeah, like mind blown doubly just out there. Thankfully, these are hypothetical, so we can scratch off most of that craziness from the list of experimentally confirmed particles. Wrapping up here, we have the magnetic monopole. It's a fairly generic term. There should be also anti-monopoles, though it's unknown if there's superpartners. And then preons would be subparticles of quarks and leptons, but these are very unlikely due to experiments that have all but ruled them out. Quarks would have 3, Y bosons would have 6, and there could be plus, anti-plus, 0, and anti-0. Okay, next we have quasiparticles, things that aren't actually particles, but sort of act like that in certain situations, or it's helpful to consider them kind of like particles in modeling or whatnot. So anyways, we have anion, plecton, polaron, bipolarion, skyrmion, sounds like a video game, hophion, sounds like an ancient civilization, electron hole, electron quasiparticle, exciton, bogoliabon, sounds like an exotic location, leviton, orbiton, spinon, trion, plasmon, plasmaron, phonon, and phoniton. So there, I'm going to just all give them like two letter abbreviations and break out their outline to show the quasiparticles. Starting with anion, it occurs in 2D systems. It's not like a fermion or bosons. So I think those are abelian, and I think the correct term for anions would they be non-abelian. So plectons are a generalization of anions, I believe, to 3D. Polarions are moving charged quasiparticles surrounded by ions in a material, while bipolarions are a bound pair of two polarons. Skyrmions are a topological solution of a pion field used to model low energy properties of the nucleon. Hophions are topological solitons. We'll see solitons in a little bit, but another thing is they're a 3D counterpart of the skyrmion. Electron hole is lack of an electron in a valence bond, where an electron quasiparticle is an electron that's affected by other forces and interactions in the solid. An exciton is bound state of electron and electron hole. Boligal bond are broken Cooper pairs. That's a pair of electron or other fermions. Leviton is a collective excitation of a single electron within a metal. An orbiton is resulting from electron spin orbital separation. A spinion is produced as a result of electron spin, charge separation. Trion is coherent excitation of three quasiparticles, two holes in one electron or two electrons in one hole. Plasmons are coherent excitations of a plasma. Plasmarons are emerging from a coupling between a plasmon and a hole. Phonons are vibrational modes in a crystal lattice, and phonitons are a theoretical hybridization of a localized, long-lived phonon and a matter excitation. And of these, phonitons are hypothetical. The rest have been observed in some degree or another. Rounding out our list of quasiparticles, we have solitons, baryons, oscillons, polarons, polaritons, dislons, phasons, rotons, magnons, wrinkleons, configurons, dropletons, fractons, holons, pneumaticons, sounds like a science fiction convention. And again, I'm going to just make up 2-letter acronyms. So a soliton is a self-reinforcing solitary excitation wave. A baryon is a bound state of solitons, named for the Born infield model. Oscillons are soliton-like single waves in vibrating media. Polarons are moving charged quasiparticles surrounded by ions in a material. We've seen something like that before. Polaritons are a mixture of photons with other quasiparticles. Dislons are localized collected excitations of a crystal dislocation around static displacement. Phasons, vibrational modes in a quasi-crystal associated with atomic rearrangements. A roton is an elementary excitation of superfluid, helium A. Magnons are coherent excitations of electron spins in a material. Wrinkleons are localized excitation corresponding to wrinkles in a constrained 2D system. Configuron is elementary configurational excitation in an amorphous material involves breaking a chemical bond. A dropleton is a quasiparticle that behaves like a liquid. A fracton is a collective quantized vibration on a substrate with a fractal structure. Holons result from electron spin charge separation. And then pneumaticons are a soliton in a pneumatic listed crystal media. Woo! We made it through. Let's get dark matter and energy out of the way because that makes up a lot of the observed universe and we're really not sure what it is. And by we, I mean physicists, which are much smarter than I am. But anyways, here are some candidates. On the dark matter side, there is WIMPs, which is weakly interacting massive particles. Some candidates would be the lightest Kaluuya-Klein particle, the lightest T-odd particle. There's WISP, which are weakly interacting sub-eV particles. They can be also known as slender or slim particles. They're the counterpart to the WIMP. The GIMP is the gravitationally interacting massive particle. The SIMP is strongly interacting massive particle. SMP, stable massive particle. FIP, feebly interacting particle. And LSP is the lightest supersymmetric particle. That could also be a WIMP. It can't be an S neutron, so that's a supersymmetric neutron, or neutrino or gravit, but it could be maybe a gravitino. It's really not clear what it could be, but those are some ideas. Then there is also the symmetron. Over in dark energy, there's the chameleon, which is a scalar particle and has a variable effective mass. There's an acceleron related to the mass of the neutrino, responsible for the accelerating expansion of the universe. And going back again to the symmetron, it would supposedly mediate a fifth force and be responsible for invisible barriers in space. And this was a newly hypothesized particle I learned about as I was wrapping up this thing. So that's an interesting cutting edge development here. And I'm going to just have a bunch of particles that I throw numbers at to make it look like they're particles. But these are, of course, all hypothetical. Okay, some various other ones that I couldn't really fit anywhere else. Just get them out at the end. There is the Baryon. It travels slower than light, and it's non-zero. It has a real rest mass. So this would be a category. So this is really all matter, most matter, like, you know, things like quarks and not leptons, but not things like photons, which travel at the speed of light. So a luxon travels as fast as light and has no rest mass. So those are things like photons, gluons, and gravitons. The real hypothetical one is the tachyon. You've probably heard that if you read science fiction. It's a very science fiction thing. It would be travel faster than light. It would have an imaginary rest mass. It has not been observed. And of course, it would violate causality. So that's probably why we won't find it. Other ways of sort of defining particles, we have the caloron. It's finite temperature generalization of instantons. There's geons, EM, or gravitational waves held together in a confined region by gravitational attraction. Instantons, field configurations with a local minimum of the Euclidean action. The pomerons, sounds like a hair product, but also is used to explain electric scattering of hadrons and local of reggae poles. Apparently, there's a thing called reggae theory, not the music. There's sphelerons, field conversions were a saddle point of Euclidean actions. Then there's Goldstone bosons, which I think some of the particles like majority and fermions would be technically goes on bosons. There's also Goldstinos that would go into that, the supersymmetric partner. They're massless excitation of a field that has been spontaneously broken, and yeah, it has a super partner. There's the dion, hypothetical partners with both electric and magnetic charges. Mini-charged particles, charged with tiny fractions of electrical charge. Continuous spin particles, hypothetical massless particles related to the classification of the representation of the Poincare group. So all of these things here just gets nice little particle representations. A tachyon here, of course, is going to be hypothetical, as well as a continuous spin particle and mini-charged particles. With that, we've gotten through here references. I'm sure I've missed some particles or mischaracterized them, but this was all the particles I could possibly find, characterize, and be enamored with.
Wasn't that a nano-sized adventure? We now know every particle, and knowing is half the battle. The other half, of course, is bracing yourself for awesome. Thanks for joining.